My name is Benjamin Arbert, and I'm going to lead you today through our webinar. I would like to show you today the features of the FVA-Workbench, the FVA-Workbench 9, and the latest features. Our webinar is going to take about 1 hour, and you are welcome to ask your questions today via the questions section in your side panel. I would be happy to answer them in the end, and would like to start with the release announcement. We're happy to announce that our release was on February 13th. So on Tuesday, we published our FVA-Workbench 9.0 with some exciting new features, and that's what I'm going to talk today. I would like to start with some sentences about operating states, then how we are going to consider backlash and backlash deviations, the new functionality of multi-part housings and interference fits, as well as additions to our bearing calculation. Then I would like to finish with some improvements regarding the bevel gear pre-design. Let's start in the beginning with operating states. We know that our machines have operating states, and most of the time they are clear from the beginning of our projects. And most of the time we want to consider them in one calculation. In the past, the FVA-Workbench had the functionality of considering one steady state operating point as a default operating point. And with the new functionality, you're now able to include all the operating points. And all the details of the simulations are visible via our model snapshots. So how to use the new features? We have included a new editor to use the operating points, or to input the operating points, and every operating point has a name, and I would like to highly encourage you to use that to afterwards identify the operating point. Every operating point has a power flow organized in lines in the editor. You could include a timeshare, what timeshare this operating point has in your design, and an effective temperature, lubricant temperature. And I would like to, obviously you could also add additional loads. And I would like to give you an overview and compare it to the functionality that we have currently. What we call the scaled load spectrum is very versatile for big load cases. And you could scale the load. For your load case, you could scale the rotational speed. However, if you would like to add additional forces or bending moments, it gets a little bit tricky. It's not possible to add lubricant temperatures or get a report for each load case. And we fixed that with what we are calling flexible load spectrum. With the flexible load spectrum, you can take all these effects into consideration. And I would like to do that with a live demonstration. Here we have a reduction gearbox of a rolling mill measured in FVA, in the research project FVA 131. And what you can see is the load over time. We can see that in the middle section, this is the rolling process. The beginning of the rolling process, when the slab enters the process rollers, we get a torque peak of a factor of 3. And when the slab exits the process rollers, the inertia leads to negative torques. And we can take that into consideration as well. So we are adding three steps: the beginning of the rolling process, the rolling process itself, and the idle time. And I would do that with the FVA-Workbench. Here we have a herringbone gearbox, 2 stages. And if you would like to use the flexible load spectrum, you can access the flexible load spectrum via the load spectrum or via the load spectrum. And below the scaled load spectrum, here's you can find the flexible load spectrum. This changes the power flow section of the editor. And here you could see I already inputted our 3 load cases with all the data that we've seen. And now I could start the simulation. And the simulation will go through all 3 load cases and add a snapshot, a model snapshot to the model snapshots. And here we can access all the information. So within the model snapshots, you will see the pressure on the flank. You can access the service life for your bearings and the shaft safety factors. And in addition to the simulation of all 3 load stages, we get a 4th model snapshot containing all accumulated values. Here we can see the model snapshot with the accumulated values for the flank safety and foot root safety. And if we're looking here in the cylindrical gear section, we can see that both flanks are loaded. The right flank is loaded with the beginning of the rolling process and the rolling process itself, and the left flank is loaded with the inertial moment from during the idle stage. And as I said, we can also access all 3 of our load cases. Here we can see all the data that we've simulated, and we can access it and have a look at the data to make sure where our damage is coming from. So let's go back to our presentation and summarize it. So the advantages of the flexible load spectrum is that we can have complex power flows, meaning if you have a complex machine with multiple power outputs or multiple power inputs, you can take them into consideration and build it in a load case. Each operating state has its own power flow, meaning that you could configure your power flow in such a way that all the APUs are taken into consideration during the right operating state. This significantly improves the evaluation option, meaning that you can dive deep in each load case and evaluate where your damage is accumulating. And if you like the functionality of the scalable load spectrum, well, it's still there. The functionality is still retained. So I would like to switch the subject a little bit for backlash. You might know what backlash is. It's the distance between the back flanks, the rear flank with the next flank. This is the backlash in the gears. And especially if you're looking for low backlash solutions, it's interesting to know how much backlash you will have with a certain design. And it is now possible to consider the backlash in the mechanical system. You can find this option in the gear unit under control parameters. And here you can see the option consider backlash in the mechanical system. And what this option does is it adds a constant modification of the minimum or the maximum normal backlash to the tooth height. And you will see that in the torsion of the gearbox giving in the default output. And we're going to have a look at this later in the demonstration. So what is the effect? Here we can see that in earlier versions, we always simulated without any backlash consideration. And the torsion here for this model is 0.1 degrees in total for this load case. If we consider the minimum backlash, this increases to 0.35, and for the maximum backlash to 0.51. So here you have the option to take both options into consideration, the minimum backlash and the maximum backlash. For planetary gear sets, it is important to also take the backlash deviations into consideration. And this option is now available in the planetary gear stage on the main geometry. Here you could see the options for normal backlash deviation or transverse backlash deviation. You can choose one of those two. For this instance, we have a planetary gear set with 3 planets. So we have 6 individual meshes, and you can input a normal backlash deviation for each mesh. And you can expect one of 2 system responses by doing that. In the first case, we have a very small gearbox with 55 millimeters in diameter with a very flexible sun gear shaft. This design has a gear ratio of 10, and I'm expecting a deviation of our sun gear shaft and no changes in the load distribution across the planets. And this is what we can see here. I inputted a large backlash change of 30 microns for the first mesh between our sun gear and the planet. And as expected, we are not seeing any changes or hardly any changes in the pressure distribution for all planets. However, we can see that the bending line of our planet gear changes quite drastically. The second system response is for models where we have a rather rigid sun gear shaft and rather flexible planets. In this case, we have a gear ratio of 3, with an outer diameter of 65 millimeters, so it's in the same range. And as expected, the sun gear shaft is not able to compensate for the deviations that we inputted in the same mesh. However, the changes are within the maximum pressure, and we can see that for the first mesh here, we have a change in maximum Hertz pressure of about 100 Newton per square millimeter, which is quite drastic. So I would like to show you this also in the FVA-Workbench, so that you can see where these inputs are located. Here I have built up the model that we've seen before with the 3 planets, and the normal backlash deviation I would like to input again 30 microns. And by starting the simulation, I'm adding a new model snapshot, and we're calling it backlash deviation. I'm setting the nominal geometry that I simulated before as a reference, and we can compare the reference. And as expected, here we can see that the changes in pressure distribution are marginal. They're not significant. However, the sun gear shaft bends quite extensively for this small design. We have a maximum deflection of 1 micron, whereas the nominal geometry has a maximum deflection of 0.02 microns, which is about 0. Then we can also add the backlash in the gear system. And I would like to add the minimum normal backlash, restarting the simulation. And we again compare it with the nominal geometry. And before we had about just can have a look. Where before had barely noticeable influence on the torsion, we can see that the torsion of the gear system doubles by taking into account the backlash. The next subject is regarding multi-part housings. So with the older versions of the FVA-Workbench, housings were considered as one solid, and during the import of the solid, we merged all the parts of the casing to one geometry and meshed it as one geometry. However, errors when joining the components could lead to difficulties in meshing, and if you would need a very fine mesh due to fine geometries, you would have the fine mesh everywhere, where possibly some parts of the housing wouldn't be relevant. For example, some covers or some unloaded parts. So now you have the option to mesh less relevant components in a coarser mesh, and more relevant or more detailed components in a finer mesh. And as a secondary effect, it is an important extension for us to incorporate, for example, bolts in the future, so that we can have more detailed housing models. For the moment, however, the housing behaves as usual, as you know it from older versions of the FVA-Workbench. During the import of your housing geometry, we recognize the bodies as solids and import them as subcomponents of a finite element component. In a second step, you then could mesh them and also define the contact. And that's what I would like to show you in the presentation. So importing the housing, as we said, recognizes the solids. Then you could mesh the components independently, or as in the past, as one component. You could then position the geometries, input the contact area, and then determine the housing stiffness using the finite element method. And this is the GUI, the user interface. So here you see the 7 steps required to perform to take the housing into consideration. The contact definition, this is the new step 6, is very simple. So you could select the first component that you would like to establish a contact. Then you would select the second component where the contact is located between. And afterwards, you would select 3 nodes on the surface of the contact. And those 3 nodes establish a surface or establish a plane where we are looking for contact nodes. Then you could select snap contact nodes, and the contact is taken into consideration. And this might be a little bit too quick, so I would like to show it to you again. Here we have our easy entry model. You might be familiar with this model. I already imported the CAD geometry, and here, as we already discussed, below the casing you see 2 FEM subcomponents, and with those subcomponents you could individually mesh them or check the FEM quality, the mesh quality. I would like to run the FEM measure in total for the whole casing. I'm running a quadratic mesh in standard. Create the volume mesh. The mesh is already positioned, so I would skip step 3 and determine the mounting points. For the mounting points, I'm selecting 1 node on the bottom and automatically select all nodes on the same plane. Selecting the nodes with finish. Then step 5 is snap finite element coupling nodes. Here we are selecting the nodes that are where we have a contact between the bearings and the housing. We agree with finish, and now we have the new option snap finite element contact nodes. Here you see brackets optional. optional in this instance means you don't have to do it if you have one single body. However, if you have multiple bodies, we highly recommend to perform this step in order to make sure that the housing is not falling apart during during the simulation. Otherwise, you might have difficulties reaching convergence during the simulation. As described, I'm selecting the first part, selecting the second part of the contact, and to make it a little bit more easy for me, I'm going to hide the upper part of our casing. Then I need to select 3 nodes that describe the plane of the contact, and select catch contact nodes. And now we've selected all contact nodes for our housing. And then we can click calculate stiffness as a 7th step, and this concludes the multi-part housing. Again, this allows you to import quite complex housings and mesh them in accordance to each part of the housing. So each part of the housing can have a little bit different meshing characteristics, and it's not required that you measure it in total and as a whole geometry at once. Okay, let's go back to the presentation. I would like to talk a little bit about our interference fits. The interference fit in the FVA-Workbench is based on the FVA simulation tools, and those are based on the DIN 7190, and in the DIN 7190, a ideal plastic material behavior is assumed. However, this is a gross simplification of real material behavior, and we added a more accurate representation of material behavior by adding also another material model. So now you could add a stress strain curve with a new stress hypothesis. So the DIN 7190 had a modified shear stress hypothesis as a basis, and we now added a shape modification hypothesis, von Mises. The von Mises hypothesis is well known in the industry, and from what I know, it is the most used stress hypothesis. So I think it's a good assumption to use the stress hypothesis according to Mises. And if we're looking at the differences in the results, we can see that the modified shear stress hypothesis and the shape modification hypothesis have about the same results if we are in the linear elastic region. However, if we have a partially plastic behavior, the results change quite drastically. Let's also talk a little bit about bearing calculation, and I would like to talk about the SKF calculation service. We're using the SKF calculation service for a couple of releases, and we used to support the stiffness simulation and the service rating life simulation according to ISO TS 16281. But we now added also the SKF rating life, the friction and power loss simulation, and also the rolling frequencies and static safeties. The benefit of the SKF calculation service is that SKF is calculating on their service with the real geometry, including the profile of the rollers and also the oscillation for ball bearings. So you don't need to rely on our internal assumption of a certain geometry, but you could rely on the real geometry that SKF is providing. SKF is getting the bearing name and the load from the system simulation, and the only parameters or the only input from your side is your SKF account credentials. You can register at skf.com for a My SKF account. It's for free, and then you can input the credentials into the FVA-Workbench, and then you have access to all the simulations here. And I think it's quite beneficial here to use the SKF calculation because of even in a very early stage of your gear design your gearbox design project, you can get feedback from SKF and without contacting SKF directly, but you have access to their results and their simulations. And I was interested in the differences between our internal simulation and the SKF simulation, and I did a comparison between those. In a best case scenario, so this is the input shaft here for 4-stage parallel shaft transmission. We have a deviation in deflection below 7%, which equates to 13 newtons, which is negligible. For the middle shaft here, it's still quite well fitting. You can see a delta U, so the actual deflection of about 6%. However, looking at the values here, it's about 3 microns, which I think is a quite good fit here. There are also considerable differences here in the output shaft. We have a difference in delta V of about 41%. However, 41% here equates to 2.6 microns. Seems like a lot, but in absolute values, I think it's quite fitting here. For the internal simulation, we also made a couple of major changes. We removed the FVA bearing catalog. The FVA bearing catalog is a very old catalog where we recalculated the inner geometries, or we estimated the inner geometries of catalog bearings. And it used to be a option to simulate the ISO TS 16281 with catalog bearings. However, due to the fact that the load rating for the bearings changed quite significantly in the last 10 years, we removed the FVA bearing catalog. Instead of that, we added the option that you could use the ISO TS 16281 with catalog bearings, so you can select the option to use the estimated inner geometry. In addition, we also added the the catalog calculations for minimal load, permissible speed, and permissible axial load. So you have a full catalog load rating for your bearings as well. And finally, I would like to talk about the GUI improvements, and those are, well, most significantly for the bevel gear geometry pre-design. The bevel geometry pre-design is a very potent tool to get a geometry in accordance with ISO 23509, and also generate the microgeometry and a manufacturing file. And with those information, with the microgeometry and the manufacturing file, you could jump into the localized load rating within the FVA-Workbench in a seamless process. So from a blank paper to a very highly detailed calculation within 1 or 2 steps. Here we changed. We had this feature for 2 releases, I think. However, it was a little bit cumbersome to use, and we changed that quite drastically. Here you could see we added default values, and could, for example, here you could choose the geometry of your taper, how the gear is designed across the width of the gear, with a constant slot width or with a modified slot width, and this equates to various manufacturing machines or manufacturing machine capabilities. We also added the outer circumferential backlash, and this is calculated from the accuracy grades 4 to 7 or 8 to 12. So you don't have to look in a table and calculate the outer normal backlash from that, but we can do that for you. And also the basic crowning could be user specified, or you could calculate it according to Niemann-Winter, which is quite handy. So this is, in my personal opinion, I try to avoid the feature in the past, to be honest, most of the time, because I was afraid that I'm not able to input the correct values for presentations. With the changes that we made in the GUI and for this feature, I now feel very comfortable to show this feature, show it in presentations, and show the power of the feature. I think this is a very potent feature right now. And that brings me to the end of my presentation. And I would like to ask you for your questions. I see that we have a couple of questions here. If you have additional questions, please let me know. You can input them into the questions tab on your side panel, or you could contact me later via my email address or by phone. So let me see. Are any new licenses required for the features? Thank you for the great question. No, all the features that we've seen today are included in the licensing packages that you might already own. So the load cases are included in the load spectrum calculation. The bearing simulations are included in all editions of the FVA-Workbench. The bevel gear simulations and the pre-design are included in the localized bevel gear simulation. And the backlash simulations, as I showed them, are included from the extended edition of the FVA-Workbench. So if you're using one of those editions, no additional licenses are required. Is it possible to use a housing with more than 2 parts? Thank you for the great question. Yes, you could have a housing with as many parts as you want. But please keep in mind that for every interface between the housings, you need to define a contact. And what I've shown you today with a multi-step process to define the interface, for each interface you need to do that. Otherwise, you might risk that the gear system is not converging in the simulation, or the housing is drifting apart. And this might be a clue for you if you're using multi-part housings, that you're missing an interface there. Did I understand correctly that there are no additional fees for the SKF calculation service? Yes, that's true. The SKF calculation service is included in the FVA-Workbench, and you are free to use it with all editions of the FVA-Workbench. The only thing that is required is a MySKF account, and you need to input the account credentials into the FVA-Workbench. But from that point on, it's completely free of charge for you. And I would be happy to hear from you what your experience with this service is. So that seems to be all from your question side. We are a little bit early, and I would like to encourage you, if you have questions in the aftermath, please let me know. You can contact me, and also if you would like to follow us on our newsletter, you will get all the information. And if you have some colleagues that would want to participate in today's webinar, but they were not available, we're going to inform you via our newsletter when the recording of today's webinar will be online, and they can rewatch it then. That would be all from my side. I thank you very much for your time, that you took the time today for our webinar, and I would be happy to hear from you. Have a great day and hear from you soon. Bye.